Good afternoon, and thank you for joining us today as the National Board of Public Health Examiners presents the final CPH review session webinar geared towards explaining the Certified in Public Health Credential, the CPH, and help you prepare for the upcoming exam. This session will be 2 to 3 hours long and include a presentation, lecture, and interactive segments. A break will be offered midway through the presentation, and this presentation will be archived on MBPHE's website. Today's session feature is Biostatistics. We are pleased to have Dr. Sumi Suzuki, Associate Professor and Interim Department of Biostatistics and Epidemiology at the University of North Texas Health Science Center School of Public Health. Dr. Suzuki?
Thank you very much, and good afternoon and good morning on the West Coast. Let's go ahead and begin. What I want to do today is go over sort of the content outline that you have, as well as some of the materials for the CPH exam. I am currently a faculty at University of North Texas Health Science Center. I have been writing and modifying the contents of the CPH exam for a few years now, so I have a little bit of an idea of what the exam looks like. So just a preface and overview first. So what do I want to do with today's presentation? I want to give you an overview of biostatistics material based on the CPH content outline available online. Today's lecture or today's presentation is intended to be only a refresher in biostatistics. It's not meant to be a comprehensive lecture or course. As such, I am assuming that you have taken and passed an introductory, at least one introductory biostatistics course in your course of your MPH studies. So I'm going to focus on the main ideas and methods. I'm not going to focus too much on the mathematical detail or the theoretical aspects of it. You can take a look at those in your textbooks and other resources. But really the main idea today is focused on some of the big key items for the exam that will probably be on the exam. Let me talk a little bit about the CPH exam, or specifically the biostat section of the CPH exam in general. As you might know, there are a total of 200 questions or items on the CPH exam. 30 questions or 30 items of it are labeled as biostatistics items. Now, some of them might seem like biostatistics, but as you know, certain areas of public health blend together, so some questions which you may see in biostatistics may actually be labeled as epidemiology or vice versa. But technically speaking, there are 30 items that are biostatistics items on the exam. Each item is mapped to one and only one content area of the CPH biostatistics content outline. So any question on the exam should be linked to a content outline area on the outline. I would study the material or related topics from the content outline and not just the material from your Intro to Biostat course. Different schools and different universities will cover different material at different rates. They will use different books. They will emphasize different things. So go by the content outline and study those material in conjunction with your material from your intro course. All items on the exam are multiple choice. There will be a question followed by 4 possible answers. There will be only 1 correct answer and 3 what we call distractors or incorrect answers. So if you see that there are or there may be 2 viable choices, you should choose the best one. Best one may mean the most commonly used one. Sometimes you may see an item where you say, well, both choices are in fact correct. But ask yourself, well, which one is the most conventional or which one is the best answer out of the 2? There are no calculations required for any question on the CPH exam. You are not allowed to use a calculator or any other resource. So we do not expect that you are going to do any calculations on the exam. So what will happen is that if there are questions that require calculations, it will be listed in equation or formula format. I have an example here. A very simple question. If we donate a total of $100 to 4 charities equally, obviously the answer is 25. But on the CPH exam, the answer will most likely be written as 100 divided by 4 and not 25. So we don't make you do calculations in general. Very simple things like what's 10% of 100, those things you may want to know. But in general, there are no heavy calculations on the exam. Everything will be written out in equation format. The content outline I mentioned can be accessed through the website that I posted there. It's a PDF file. It's the content outline for the entire exam, not just biostatistics. Many of you probably have already seen that, but there is the link to it if you have not had a chance to look at it. For the exam itself, there may be things on the exam you may not have covered in your class, or you may think that it wasn't part of the content outline. But just be assured that we grade the exam as a whole, so you don't do badly or you don't fail the exam just because you missed 1 or 2 questions on the exam in any section. You do badly if you do badly on a lot of problems. So as long as you're showing a general competence in introductory biostatistics, you should be fine for the biostat section of this exam. The first thing I want to do, though, is if you had a chance to look at this content outline, you may notice that many of the topics on there are very broad or just a short description. And you may be confused as to what we mean by those bullet points listed on the content outline. And even some faculty are mixed in terms of what we mean by that. So I kind of want to take the first 15, 20 minutes or so just going over the content outline for biostat and telling you what do we really mean when we say certain things on the content outline. I'm going to go by number. I'm going to closely label it as much as possible here. But when I say BIOS 1, that means Biostatistics Content Outline number 1, and it should be titled Visualizing Data. Okay, and each subsection is labeled A, B, C, and so on. So for visualizing data, the first thing you see is data presentation. Data presentation means graphical representation of data. Okay, data, as you know, will come in a spreadsheet or they might come in data collection forms. But when we're talking about visualizing data, we usually mean some graphical representation of data. Okay, I put some common ones up here. We'll go over some of these a little bit more in detail later, but you might have bar plots for categorical data. You might have histograms for continuous or ordinal data. You might have a box plot, or some people call it a box and whisker plot for continuous data, possibly with outliers or skewed data, but it doesn't have to be. The second thing, Kaplan-Meier. This is a curve used for survival data or survival analysis. It's actually a method, not a curve, but there are things called a Kaplan-Meier curve. I'll go over this at the end, and I understand that some intro biostat courses never get to survival analysis. Some do. So this may be new to you, but this is one of the content areas, and we'll talk a little bit about this toward the end of the talk. Simple regression lines. You definitely have had regression in Biostat 1. For visualizing data, all this means is that can you understand that a regression line or simple regression line is simply a line or a linear relationship between some independent variable x and a dependent variable y. Number 2 on the content outline says descriptive statistics. These are now numerical summarizations or numerical representations of summary statistics. Okay, usually these are not graphical. So when we talk about descriptive statistics, we can talk about describing certain parts of the population. So the first one, A, there's central tendency and variability. So these are common measures used to describe central tendency and variability of a population. So for continuous data, you might have something like mean, median, or mode. For variability measures in continuous data, you might have standard deviation. You might have variance, which is the square value of the standard deviation. The range, which is the distance from the minimum to the maximum, and interquartile range, which is the distance between the first and third quartile. If you have categorical or ordinal data, which means you have counts, you can use the raw counts. How many of each category do you have? You can use proportion or percentages to represent the proportion of a certain category that you have for a variable. Percentiles, you want to know the definition. We'll go over that a little bit later. The main point is that the first, second, and third quartiles are actually percentiles at the 25th, 50th, and 75th percentiles. Standardized scores, some will argue that this is not really a descriptive statistic. This is part of inference, but usually when we talk about standardized scores, we're talking about standardizing an observation by subtracting a mean and dividing by its standard deviation. You use this technique more so when you are constructing test statistics for hypothesis tests. Number 3, statistical probability distribution. You see different distributions on there from A through F. Some you have to know a little bit more in depth than others. Namely, the first one, the normal distribution. You're going to use this a lot throughout any intro statistics course. So you want to know the fact that the shape of the normal curve is symmetric, it's bell-shaped, that the median, mean, and the mode are the same. You want to know the 68, 95, 99% rule. You want to know that the distribution is defined by two parameters, the mean and variance. And there's such a thing as called a normal or standard normal distribution, which has mean 0 and variance 1. And we'll go over some of this a little later too. The next one, T distribution. You certainly want to know the shape, but really the application that we're looking for with the T distribution is when you use t-tests. So you're going to use t-tests to compare means, or you might use a t-test as part of the regression test for slopes. Okay, so we're not really looking at the depth of knowledge about the T distribution as much as the normal distribution. We are just looking to know that you understand that the T distribution is used for t-tests. Binomial distribution, okay, these are used to model categorical data, two possible outcomes of yes or no, and it's actually a counting process or counting distribution where you count the number of yeses or successes or events, whatever you're trying to count. Under a fixed number of trials. So it means that if you, for example, flip a coin 100 times, how many times does it land on tails? Okay, the number of times it lands on tails will have binomial distribution with a certain probability of success. Okay, if the coin is fair, that p would be 0.5. Continuing on with statistical probability distribution, the chi-square. Again, you do want to know a little bit about the shape of the chi-square distribution, that it's the fact that it's a skewed distribution, not a symmetric distribution. But the main application we're going to be looking for chi-square distribution is when you use it for a test of independence or test of homogeneity or a goodness of fit test. Okay, so like the T distribution, we're looking for chi-square distribution in terms of can you apply it to a test. The Poisson distribution, E, this is another counting distribution. It counts the number of events, but instead of a fixed number of trials like the binomial, it will have an infinite number of trials. You might say, well, how can there be infinite number of trials, you can think about it as number of events during a course of 1 hour. During that time, you don't know how many events are going to occur, so theoretically, you can have as many events as you want. Okay. However, usually the application for a Poisson distribution is for rare events. So not just specific to the CPH, but when you're asking questions about a Poisson distribution, a key phrase that you may look for is rare events. We tend to apply Poisson distribution when the occurrence of an event is rare, okay, meaning low probability of occurring. And then lastly, the F distribution. Again, you might want to know the fact that it is a skewed distribution, but again, this is one of those distributions that you are going to apply for different tests, namely the ANOVA F test in either a one-way ANOVA or a linear regression to test, well, in ANOVA, whether several group means are the same or not. In regression, you're going to test whether the slopes are 0 or not. The other application for the F distribution might be to test equality of variance. So you have two populations, and you may want to test an equality of variance between those two distributions. An F distribution can be used for such a test as well. Moving on to 4, variables and measurement scales. The first one, I think, is a little bit confusing. It says qualitative versus quantitative variables. You might have seen words like categorical, dichotomous, or binary, and ordinal variables. So essentially, qualitative variables are variables that are can be listed in terms of groups or levels or categories. And by quantitative variables, in general, we mean all continuous variables. So those are some of the more specific type of variables you want to know and what we mean when we say qualitative versus quantitative variables. Okay? And as an application, you want to know when or what variables are categorical, dichotomous, ordinal, etc., as well as what type of methods in terms of hypothesis tests, what type of methods in terms of descriptive statistics would I use when I have such a data. The next one is confounding. I'm sure you had confounding in your epidemiology review as well, but we've talked about it in biostatistics as well because it is very important. And it's a third variable that masks the true relationship between an exposure and an outcome. So when I say exposure and an outcome, I'm using more terminology that's more common in epidemiology, but in biostatistics we may more often call it independent and dependent variable. So the exposure would be the independent and the outcome would be the dependent. The main aspect of confounding that you may want to know is that through statistical methodology, we control for confounding either through stratification of the confounding variable or through use of multiple regression, meaning you include the confounding variable or the potential confounding variable in the regression model of the analysis. C, effect modifiers. Effect modifiers means, or effect modification means that the effect that the exposure has on an outcome, or the independent variable has on the dependent variable, depends on level or values of another variable. Okay, so it means that if a drug affects men and women differently, then gender would be an effect modifier for the drug's effect on a person. As I've already mentioned, independent versus dependent variable. Okay, the dependent variable is the outcome of interest. Other terminology that you might hear synonymously with outcome is response or output, or in epidemiology terms, outcome. But in statistic terms, we usually call those dependent variables. The independent variable can be called an exposure, it could be called a predictor, it could be called a factor of interest, but essentially we're trying to determine the relationship between the independent and dependent variable. More specifically, how does the independent variable affect the dependent variable? Measurement scales. These talk about the level of information or the amount of information in a variable. Going from nominal, ordinal, interval to ratio, there are increasing amounts of information. So there's more information from a variable with a ratio scale as opposed to interval or ordinal. And we'll talk a little bit more about that because that could be somewhat of a confusing thing for some of you. 5 is measurement. So we talk about two things, reliability and validity. Reliability is consistency of the measures. So under similar conditions, can you produce similar results? Okay. Think about it as like you get on a bathroom scale. Okay. And your weight hasn't changed, but is your weight scale actually giving you the same measurement each time? If it is, then it's reliable because your weight hasn't changed, meaning the conditions haven't changed. And if the results are similar all the time, then it's reliable. It's consistent. Okay? What you would want to know for reliability is probably the concept of reliability that I just mentioned. In addition, you may want to know about Cronbach's alpha, which is an indicator of internal consistency or internal reliability, but that's a sort of an elementary measure for reliability that some people use for questionnaires and things like that. Validity usually goes right along with reliability. They mean different things. Validity is the actual accuracy of the measure, or how true is your measure, meaning the result you've gotten, is it actually what it was supposed to measure, and is it giving you an accurate number? So going back to that bathroom scale, if somebody who is 200 pounds gets on the scale, does the scale actually read 200? Okay. If it doesn't, then it would not be a valid measurement. Okay. Number 6 is estimation. I kind of grouped it with number 12. Okay. Because they go hand in hand, and I would like to apologize. On number 12, I didn't write the content outline, but on the content outline, number 12 is misspelled. It should say confidence intervals. It's not confidence internals. Okay, so number 12 on the content outline is confidence intervals. And that goes hand in hand with estimation, which is number 6. Okay. So from estimation and confidence intervals, what you want to know are sampling theory, meaning sampling distribution, distribution of X bar, things like that, and how it relates to central limit theorem. Central limit theorem says that the sample mean follows a normal distribution as long as the sample size is large enough, and, well, if it comes from a normal population, it already follows a normal distribution. Estimation of population parameters. When we make conclusions about populations in statistics, what we're actually doing is making conclusions about parameters of the population. Okay, so parameter is some unknown feature of the population. So the mean of the population is an unknown feature. The variance of a population is unknown. The median is unknown. All these things are unknown features or characteristics of a population. And you use statistics to estimate those so that you can conclude something about the population. Okay? So to make conclusions, the first thing we usually do is estimate that parameter. Okay? And usually this is fairly straightforward. You use a sample version of the parameter from your observations that you got from the population. So for example, if you wanted to estimate the population mean, you would use the sample mean. If you wanted to estimate the population median, you would use the sample median, and so on. Okay? Now, those estimations that I just said are what's called point estimates. They use one number to estimate a feature about the population. Those are not very helpful to us because it doesn't really speak to the accuracy or the precision of the measure itself. Okay? To do that, we tend to use what's called a confidence interval. A confidence interval will give you a range of values for a parameter or feature about the population, so that we have some idea of sort of plausible values for those parameters. Not only that, we have a significance level for the confidence interval, which tells us about what level of confidence are we in making this estimation or this prediction. Okay, so that's a technique. It's often or sometimes called point estimation versus interval estimation, where the point estimation, we're talking about the sample mean itself, and then the interval estimation, we're talking about the confidence intervals. Next, again, I'm grouping numbers 7, 8, and 12. Those all have to do with hypothesis testing. Sorry, I think that's a typo. 7, 8, and 11. Testing, probability, and interpretation. But these go hand in hand, because why would you do a statistical test if you're not going to interpret them? And you can't do hypothesis testing without knowing some things about probability. Okay, so that's why I grouped 7, 8, and 11 together. Going through 7, or 8, I'm sorry, going through 8, statistical test assumptions. This is a very broad area, and it really depends on what you cover in an intro stat course, but I would think that at the very least you need to know that for certain tests to work, they have to be normally distributed, or the sample size have to be large enough for the central limit theorem to kick in for a lot of these tests. Okay. Now, if you're a little bit more advanced, you might have talked about regression assumptions or equality of variance assumptions, things like that. But at the very minimum, can you tell if the data is normally distributed? Those are some of the important things for our assumptions. Level of significance, the alpha level. This is the alpha level that you set for your tests, okay, usually at 0.05, and 0.05, and the p-value, which we compare to this alpha level. The decision errors and statistical power, we're talking about type 1 error and type 1 error rate, type 2 error and type 2 error rate, and when we're talking about power of a test, we're talking about 1 minus the type 2 error rate. Tests for group means, the z-test, 1 sample t-test, 2 sample t-test, and paired t-test, and f-test. All of these are used to test for means of some kind. The only difference would be the situation or the setup you have. And so, based on that situation that you have or the scenario you have, you're going to use a different test. Test of proportions. This is usually used for categorical data, but what you're likely to see is chi-square tests for contingency tables or tests for independence. You might also come across an equality of binomial proportions test, which will be based on a z-statistic. The goodness of fit test, again, this is one of those topics you may or may not cover in intro stat course, but we're not talking about anything elaborate here. We're talking about chi-square tests to determine whether data come from a hypothesized distribution, like a normal distribution. Okay, and so this is another application of chi-squared tests that you might have. Risks and rates, number 9. This is similar to what you had in epidemiology. It's going to be about odds ratios and relative risk. So from a 2x2 contingency table, can you calculate an odds ratio? Can you calculate a relative risk? Do you know the difference between an OR and an RR? And can you interpret confidence intervals from an odds ratio or relative risk? Number 10 lists correlation and prediction methods. Okay, correlation you use for determining the level of association between two continuous variables. Okay, it's actually very much related to linear regression, which is B. But the purpose of linear regression in general is to model the linear relationship between two continuous variables. Multiple regression. Now, multiple regression can apply to any type of regression, but multiple regression means that there is one dependent variable and more than one independent variable. So you have one y, but you have a bunch of x's. Okay? This usually happens because one independent variable is the exposure or the factor of interest, and then others are controlling variables like a confounder. D is logistic regression. Logistic regression is analogous to linear regression when the dependent variable is dichotomous. Okay, so you'll see that in statistics, what method you use or what test you use always depends on the type of setup or the scenario you have. Okay? So in terms of regression, you're looking at what type of a dependent variable do I have and what type of independent variable do I have. And that will dictate what method is the most appropriate for that situation. So logistic regression, as I said, is used when the dependent variable is dichotomous. And we like it in public health because it produces odds ratios through the regression model. Okay, for using the regression model that you have, it will produce odds ratios for any of the independent variables. Lastly, the survival analysis. Again, this is a topic that you might not have covered in intro stat course, but survival analysis we use when the dependent variable is timed to an event. Okay, so what does that mean, timed to an event? It means that you are looking for an event to occur. An event could be like death, it could be something positive like a disease is cured, but you're looking for some event to occur. Not only are you looking for the event to occur, you're looking for how long does it take for that event to occur. Okay, and so that's what we mean when we say time to an event variable. For survival analysis, we're usually looking to summarize or analyze the survival experience of an individual, okay, in terms of did the event happen, how frequent, how often, how fast did it happen, as well as comparing groups' survival experiences. So did one group fare better than the other? Okay. And this is where your Kaplan-Meier curves comes in, and maybe if you wanted to test between those two curves, you would use a log rank test. Okay. And again, I'll talk a little bit about that later on in this presentation. Okay. All right, so let us move on to some of the specifics of what we just talked about in the content outline. Okay. And some of these are not in order of the content outline. I try to organize it so that we talk about a lot of the descriptive summarization things at the beginning, and then the inferential statistics, the ones you use to make conclusions about the populations in the later parts. So just to review, what the goal of statistics is to make statements about the population based on the sample, meaning only seeing a part of a population, we would like to make a conclusion about the entire population. Okay, so a schematic looks like what you see on the slide. We have a big population. From that population, we sample and take observations from it. And based on that sample, we either describe and summarize, that's the descriptive statistics, or we apply statistical methods and tests to draw conclusions about the population. That's the inferential statistics part. Okay. During this process, we usually do two things. Okay? As I said, we summarize the data numerically and graphically. This gives us an overall picture of what's happening with the sample. The idea being that whatever happens with the sample should be happening with the population if it's a representative sample. After that, we want to make statements about the population, some feature about the population, after analyzing the data. So this part is known as inferential statistics. So this is all of your confidence intervals, all of your hypothesis tests. Now, various methods and techniques exist for both, but choosing the appropriate method depends on knowing what type of variable you have. Okay, and so the first thing I want to do is talk about variables and what type of variables you may encounter. All right. So we talked about measurement scale just briefly, but measurement scale is the level of measurement or a classification that describes the nature of information within the values assigned to variables. Okay, so essentially, a measurement scale, at least in this content, is how much information or what type of information is contained in your measurements or your variables. We're going to talk about 4 levels in a increasing order of information, from the lowest nominal to ordinal to interval to ratio. Okay. Keep in mind, these are just names given to measurement scales. All right, and I'll explain a little bit about that in a moment. But a nominal scale means that values have no inherent order. So these are variables with categories which have no order at all, like sex or gender, race, ethnicity, country of origin. These are all nominal variables or variables with nominal measurement scale. Something with an ordinal scale would have values which are ranked, give some order. Okay, so you know that depending on what value you get, one is higher than the other. However, what makes something an ordinal variable is that there is no distance or defined distance between any 2 points. Okay? I give an example. This is a pretty common example. You take a questionnaire. The answers to a question are, is it bad, fair, good? Or it could be on a 5-point scale or a 7-point scale. Okay? Now, no one's going to argue that good is better than fair and fair is better than bad. However, the distance from bad to fair is not necessarily the same as fair to good. Okay? It may take more for you to go from bad to fair, but it may take very little for you to get from fair to good. Okay? Not only that, that differs from person to person. Whoever's answering this questionnaire will have a different take on what bad means, what fair means, and what good means. But for most reasonable people, they would still agree that good would be better than fair and fair would be better than bad. So it is ordered and ranked. However, the level at which or the distance between them may not be consistent. An interval measurement scale applies to continuous data usually, and the distances between values are equally spaced. When I say equally spaced, it means that it's defined and no one's going to argue about that distance. Okay? So for example, temperature. If you're talking about temperature either in Fahrenheit or Celsius, no one's going to argue about the 1 degree difference. A 1 degree difference in temperature is always going to be 1 degree difference in temperature. Okay? At least a 1 degree difference in Celsius is always 1 degree difference in Celsius. Okay? So whether you go from 30 degrees to 31 degrees, that's the same difference as you go from 60 degrees to 61 degrees. One of the things that makes an interval scale is an arbitrary zero. What we mean by an arbitrary zero is that there is a zero because it's a number and it has distances. However, that zero doesn't really have a true meaning in terms of location. Okay? Again, I bring up temperature. There is a 0 degrees Celsius and there is a 0 degrees Fahrenheit. However, those don't coincide. They don't coincide because for each scale, the Celsius and Fahrenheit, the 0 is arbitrary. Okay? You pick a point where 0 is defined and then you go from there. The last scale is called a ratio scale. Values are equally spaced like the interval. The only difference is that now there is an absolute 0. Meaning no matter who measures it, a 0 is a 0 and it makes sense that that measure is a 0. So for example, height, weight, okay? No matter if you measure weight in pounds or kilograms or anything else, 0 pounds is going to be 0 kilograms. So that 0 is absolute. It doesn't change from one to the other. Okay? So that makes something a ratio scale. Now, one of the big confusions about measurement scale, especially because you don't just take biostat courses, you take a lot of other courses, is the terminologies that we use. Okay? especially the last one, ratio. So a ratio, in the traditional sense, is just a division of two numbers. Okay, that is, A over B is a ratio between A and B. But when you're talking about measurement scale, ratio doesn't mean that. So think about ratio measurement scale as its own entity. It's not related to a ratio variable that you might have seen in other courses, okay, or just by intuition. So when something is a ratio variable, you have to ask yourself, are we talking about the measurement scale of the variable, or are we actually talking about the fact that this is a ratio? Okay, so for example, an odds ratio is a ratio of two odds. Okay, but it may not necessarily be on a ratio scale. Okay, so once you know the types of measurement scales, the amount of information you have in a variable, you might be interested in, well, what type of variables am I measuring, and what type of variables will have such measurement scales? Okay. And again, we talked about qualitative and quantitative variables, but I'm going to break those down a little further and start with a categorical variable. A categorical variable has fixed number of outcomes, or a fixed number of categories that you can observe. Okay, and usually this refers to a nominal scale. So when we're talking about categorical variables in the traditional sense, we're talking about a nominal scale. So we're talking about gender, we're talking about race, country of origin, things like that. Okay, a categorical variable with only two possible outcomes, like gender, is called a dichotomous variable or a binary variable. Okay, and we just give those a different name because that happens a lot. An ordinal variable also has a fixed number of outcomes, but it's on an ordinal scale. Okay, so something like a socioeconomic status has 3, maybe 5 categories of low, middle, high, but those outcomes are ordinal in nature, and there's a fixed number of categories. Sometimes people would lump together ordinal and categorical together, but by the true definition of categorical, then ordinal variables should not be in that category. Lastly, a continuous variable, this is any numeric measure that's of interval or ratio scale, which can theoretically take on any value between two defined points. Okay, so for example, grade point average, okay, on a 4-point scale can be any number between 0.0 and 4.0. So that's a continuous variable. The type of variable you have will dictate the type of analysis that can be done and the type of analysis that is the most appropriate. Okay. So let's talk about how we can describe or summarize categorical and ordinal variables. Then we'll move on to continuous. One of the things you can do with categorical variables is use frequencies. So as I said, the categorical variables have no order, they just have distinct categories. So one of the things you can do is physically count the number of each category that you see. Okay? Now, maybe the counts are not as reflective of what you want to show because it just shows counts. So then you could use something called relative frequencies, which could be represented as either proportions or percentages of categories. Okay? That is, I had 40% whites, 50% blacks, 10% Hispanics, things like that. Okay? What you can do to present these are to present these in table format, okay? Or you can graph them on a bar chart. So here's a very simple example, fictitious example, I think. 6 leading causes for a child to visit an emergency room are falling, being struck by something, something environmental, poisoning, cuts, and a car accident. I've shown number of cases for every 1,000 children. Okay, so that's the frequency. And then I've calculated the relative frequency based on the total number of cases I see. Okay. So this is in table format. You can also analyze it or display it as a bar plot where this is raw counts, frequencies, of each one of the categories that you have. We could have plotted the relative frequencies, which means that the y-axis would have been percentages or proportions rather than the raw counts. Okay, but the proportionality of heights should be about the same. If you wanted to summarize continuous variables, okay, remember these are numeric variables, so they can take on any value. This is where we can talk about central tendency and variability. So with central tendency, we're asking the question, what happens in the center of the population? Okay? Or another way to put that is, what is a typical value for the population? Okay? What does the average person or the average observation for this population do or look like? Okay? We have many measures for central tendency. I'm going to talk about the three main ones that you probably came across, the mean, median, and mode. The mean is simply the average of the sample. Okay? The median, also the second quartile, is the middle value of the sample. So it's the observation that cuts your sample into the lower half and the upper half. And then the mode is the most frequent value, meaning you see this observation the most. Know that the mode does not have to be unique. You can have many observations that appear multiple times, and some may happen the same number of times, in which case you'll have two modes. Variability. Variability is how spread out are values in the population. Okay? You might have called it measure of dispersion as well. Okay? And sample statistics for variability are standard deviation. This is spread from the mean in terms of original units, or variance, that's spread from the mean in squared units, or the range, which is the maximum value minus the minimum value, or the interquartile range, which is the third minus the first quartile. Okay? Again, these are all numbers. You can present these in table format, or it may be helpful to graphically represent them. Okay? A pretty conventional way to graph a continuous data, or maybe even ordinal data, is to use a histogram. Histogram looks much like a bar plot, but because we're talking about numerical data, the x-axis actually has an order, and the bars actually show the increasing order of the values that you see. Okay. Why we do a histogram? It's helpful in determining shape of the data. Okay. Histogram shows the shape of the data, which will speak to the shape of the population. Okay. And the shape determines which numerical summary is more appropriate as opposed to others. Okay. Some common concepts that you'll see when you're talking about shapes of data, you're going to have skewness and symmetry. So symmetric means that a histogram, or the underlying population, has a symmetric shape, meaning this is not the only symmetric shape possible, but this is the most common, where you have this sort of bell-shaped symmetry. You have positive skew and negative skew, which means that much of the observation is clustered on one end or the other. Right? Why that's important to you might be the fact that central tendencies vary depending on shape. So if the shape is symmetric, or more specifically bell-shaped, the mean, median, and mode all coincide. That's all in the middle. Okay? And that's the middle picture that I have here. Okay? However, if a distribution is negatively skewed, okay, meaning more observations are on the right than left, then the median tends to be bigger than the mean, okay, and then the mode tends to be bigger than the median. Conversely, if it's positively skewed, meaning much of the observations are on the left, then you have the mean being greater than the median, and then the median being greater than the mode. Okay, so this speaks to which measure of central tendency should you use. And the general rule of thumb is that if you have a skewed distribution, mean is probably not the best measure, because it will depend on how much, where the big values are and small values are, so it may not give an accurate measure of the center. Oops. As I said, so symmetric mean median are the same, and the mode is the same. Positive and negative skew, the mean is greater than median or mean is less than median, respectively. Okay. The median seems to capture the middle or the central part of the distribution to best all three cases because the median is more robust. It's not as affected by the skewness or even outliers. So the general rule of thumb is that if the underlying distribution is not symmetric, you may use a median. If it is symmetric, the mean is probably more useful because there are nice properties associated with the mean. Another thing you can do is a box plot. Okay, some people call this a box and whisker plot, but essentially it's a box with a line, okay, and each part of this indicates a certain aspect of the summarized sample. So the tail end of it, at the beginning and the end, you're going to have the minimum value and the maximum value. Okay, so if you subtract the difference between that maximum and minimum, the range. Then in the middle of somewhere, you're going to have a box. Okay, the left end of the box, okay, or the bottom end, if it's vertical, is going to be the first quartile. There's going to be a line in the middle of the box that indicates the median, or the second quartile. And then the top of the box, or the right side of the box here, is the third quartile. And the third quartile minus the first quartile is the interquartile range. And then in the graph below, you're going to see how skewness affects these box plots. Okay? So if it's normal distribution, again, the median is going to be in the middle, but if it's positive skew, the median is going to be shifted toward the left. If it's negative skew, the median is going to be shifted toward the right. A few more descriptive statistics that you might want to know. Percentile, this is the value at which k% of other values fall below. So the k percentile means that k% of all values fall below this. Okay? So a very simple example is if you scored 90 percentile on a test, like a GRE or something like that, that means you did better than 90% of the people who took the exam at that time. Okay? And so it's a descriptive statistic that shows you sort of distribution of the data where you stand for each value. Now, we usually talk about the first, second, and third quartiles because those correspond to the 25th, 50th, and 75th percentiles, respectively. Okay, so for percentiles, know the definition or the concept of it, and pay close attention to the quartiles, which are the 25th, 50th, and 75th percentile. Okay? And obviously, the 50th percentile is also the median. Okay, so let us move on to inferential statistics. So describing the data and summarizing is all great, but you don't get to make any conclusions from it. You don't get to infer anything. You only see what you just calculate. Okay, so the true strength of using statistics comes from the fact that you are able to infer conclusions from the data. Now, how do we do that? Because we don't see the entire population. We only see the sample. What we have to do is we have to assume some underlying probability distribution for the population so that we can make conclusions based on that population distribution, or sorry, the probability distribution. The most common and most used distribution is going to be the normal distribution. And I think most of you are familiar with this, but the normal distribution would look like the following. It would be a bell-shaped curve, symmetric, okay, where a peak will be at the middle of this symmetry. There are some very nice properties about the normal distribution. As I said, the mean, and median, and mode all coincide. That happens at the peak here. Okay. Symmetric about the mean means that the area to the left of the mean is 0.5 and area to the left of, oh sorry, that should say right, is 0.5. Okay, because the area under the entire curve is 1, so the area to the left and right of this symmetric line is going to be 0.5. the 68, 95, 99% rule gives you sort of an idea of how much or how many observations fall within certain standard deviations of the mean. Okay, so for a normal distribution, about 68% of the values fall between 1 standard deviations away from the mean in either direction. So that's this area here. I don't know if you can follow my mouse, but it's around this area. If you go out 1 more standard deviation, so mean plus or minus 2 standard deviations, then you're going to have covered about 95% of all values. And if you go even further to 3 standard deviation, you would have covered 99% of all values. So if something follows a normal distributions, everyone, or most of the people, 99% of them, fall between 3 standard deviations of the mean in either direction. The normal distribution is applied or used so much because it's very easy to apply and it's very flexible. Okay, so for example, if we have an observation, I called it X, from a normal distribution with mean 100 and variance 25, then by calculating what's called a z-score or standardizing, you create a random variable or variable that has normal distribution with mean 0 and variance 1. We like this because these are the tables of distributions that's tabulated. You've used them before in your classes, and it's easy to calculate probabilities. So by standardizing, you get what's called a standard normal random variable, which is a lot easier to use. Now, what if data aren't normal? So it doesn't come from a normal population. Well, that's okay. The central limit theorem, which is a pretty powerful theorem, says that if the sample size is large enough, usually greater than 30, but that's not set in stone, then the sample mean is normally distributed. Okay? Well, even if the population isn't. So even if the population is not normally distributed, it could be skewed, it could be whatever, as long as the sample size is large, the sample mean from that population would be normally distributed. Why is that important? Because now we can standardize X bar, the sample mean, to create a normal random variable. Why that's important is because this is the usual testing procedure when we create test statistics. By standardizing, we create a test statistic with the known distribution, in this case normal distribution. So this knowing the distribution, especially the normal distribution and standardization technique, is sort of the first step to being able to conduct the formal hypothesis test in statistics. Okay. All right, I think we will take a 15-minute break at this point. We will resume right at 2:15 Eastern. I'm in 1:15 Central Time Zone, so in 15 minutes. Okay, let us resume. So we just kind of talked about descriptive statistics and summarizing data. We got into a little bit about probability so that we can do some inferential statistics. And when we say statistical inference, we're usually talking about one of two different types of inferences. One is called estimation, or interval estimation, and the purpose is to estimate some feature about the population using a confidence interval. Okay? As we talked about, a point estimate only gives you one number to describe this feature, but a confidence interval gives you a range of values, and you can speak to the precision of that estimate. Hypothesis testing is another type of inference that we do. It's probably the most common, where we start with some statement about a parameter of interest, and we use the data to determine whether the statement can be rejected or not. In general, a confidence interval and hypothesis test have equivalent information, okay, because they're both conducted from data. However, depending on our application, we use one or the other. Okay? But there is a connection, most notably if the null value, okay, the value under the null hypothesis, falls within the confidence interval, then that test will not reject. Okay? You use this a lot with odds ratios and relative risk. We always look for whether or not 1 is in the confidence interval, because 1 is the null value. All right, let's talk a little bit about confidence intervals. You can think of a confidence interval like plausible estimates or plausible values for a parameter. Okay, so practically speaking, if a 95% confidence interval for a mean, say, ranges between 10 and 15, it means that any value between 10 and 15 are, quote, good estimates for the population mean. Okay, so that's what you would probably say in layman's terms. However, technically, a confidence interval is not really that. A confidence interval's confidence comes from the fact that if you conduct this study or construct this confidence interval repeatedly for different data sets from the same population, some confidence intervals will cover the true mean, some confidence intervals won't. So in this graphic I have below, suppose this red line in the middle is the true mean. Okay, and you're going to have one of these confidence intervals. So these blue lines are confidence intervals constructed from different data sets. You're only going to see one of them. You don't know which one you're going to see. You might see this first one, which in fact covers the mean, but you might see this one, which doesn't cover the mean. Okay, so when we talk about confidence, we're talking about the fact that if a bunch of people, or if you do this repeatedly, about 95% of those intervals will cover the true mean. We never actually know if it really does contain the mean or not. Hypothesis testing. Again, this is the most common type of statistical inference. We start with two contradicting statements and try to find evidence against one in favor of the other. Okay, so the contradicting statements may be something like the mean is less than or equal to 5 versus the mean is greater than 5. It's contradicting because neither can happen at the same time, and both can't happen at the same time, and it's comprehensive. There are no other possibilities. The mean is either less than or equal to 5 or greater than 5. We call these contradicting statements the null hypothesis, denoted by H0 usually, and alternative hypothesis. We usually denote this by either H1 or H. And what we're going to do is we assume that the null hypothesis is true, and based on the data, we're going to ask ourselves, do we have enough evidence to say that the null hypothesis should be rejected in favor of the alternative? When you make a decision as to rejecting the null hypothesis or not rejecting the null hypothesis, one of four things will occur. Okay? So the true state of nature is either the null hypothesis or the alternative hypothesis. That's on this left-hand column here. So we don't know which is true, but one of those has to be true. Okay? Based on what we see from the data, we're either going to reject or not reject. When we reject and the alternative is true, we've made a correct decision. No harm, no foul. However, when we reject, but the null hypothesis happens to be true, we've made an error. We've made an incorrect decision. That incorrect decision is called a type 1 error. And we usually denote the type 1 error rate, the rate at which type 1 error occurs, as alpha, Greek letter alpha. Likewise, if we don't reject the null hypothesis and the null hypothesis happens to be true, we're correct. We make the right decision, no harm, no foul. However, if we choose not to reject and the alternative happens to be true, then we've made an error. It's an incorrect decision. And that incorrect decision is called a type 2 error. Type 2 error rate, so that's the rate at which type 2 error occurs, is denoted as beta, Greek letter beta. When we talk about the power of the test, we're talking about how often do we reject correctly. So that's 1 minus the type 2 error rate, 1 minus beta. So under the alternative, how often do we land in this correct box here? Okay. How often do we reject correctly? The usual approach to testing, you first want to construct your null and alternative hypothesis based on what you want to test. The null and alternative hypothesis usually would involve the population parameter of interest. So if you're interested in the mean, it's going to involve the mean of the population. We assume an acceptable rate at which type 1 error can occur. Okay, so we assume an error rate that we can live with. And this error rate that we can live with for type 1 error is called the significance level of the test. And the standard value in notation is alpha equal 0.05. Then we choose an appropriate test and construct a test statistic. Okay, this depends on what type of information you have and what type of variables do you have. From the statistic, we're going to compute a p-value, and then we're going to compare the p-value to our alpha value to make a decision. All right, so let's talk a little bit about p-value. So formally, a p-value is the probability to observe a value of the test statistic at least as extreme as what was actually observed. And by extreme, we mean evidence against the null hypothesis. Okay. Now, this is somewhat of an abstract definition. The way we use the p-value is used to measure the significance of a test. So it's used to determine whether we have enough evidence to reject the null hypothesis or not. If the test can be rejected, or if the null hypothesis can be rejected, then we say that the test is significant, or the findings are significant. The way we decide that is we look at our p-value and compare it to our alpha value, our significance level. And if our p-value is less than the alpha value, usually 0.05, then that means that we have enough evidence to reject the hypothesis, null hypothesis. All right. Some misconceptions about the p-value. The p-value merely indicates the chances of the result you saw, your test statistic, whenever null hypothesis is true. Okay, so it's giving you the probability of seeing what you observed under the null hypothesis. Okay, and actually it's what you observed or more extreme. So that means that a low p-value means either that the null hypothesis is true and a highly improbable event occurred. Okay, or simply that the null hypothesis is false. You don't know which one happened, but because we set our acceptable type 1 error rate to alpha equal 0.05, when it's less than 0.05, we reject. what p-value is not. A p-value is not the probability of making a type 1 error. Okay, that's your alpha level. And a p-value does not indicate the size or importance of an observed effect. Okay, so they kind of coincide, that if the larger the effect, the smaller the p-value. But different things can happen where the p-value doesn't necessarily indicate the magnitude or the importance of the observed effect. It just means what I've stated, that a low p-value means that either the null is true and we saw something very unlikely, or simply that the null is not true and we're going to reject. Okay, so knowing some of the concepts of hypothesis tests, how do we choose a test? Okay, so when conducting a test, the most fundamental question is, which test or which method should I use? And the answer usually depends on the type of variables that we have, namely the type of independent and dependent variables that we have, or what we know about the setup or the scenario. Okay, so for example, in testing whether two group means are different or not, we can think about this in one of two ways. Okay, one, we can think about it as we have a dependent variable that's continuous and an independent variable that's dichotomous, because we're comparing two groups. Okay, that may lead us to say that we should use a two-sample t-test. Another way to look at it is we have two parameters of interest, the mean of the first group and the mean of the second group, and we want to compare means. So the null hypothesis should be that the means are the same. Mean 1 equals mean 2. That would also lead to us thinking it should be a two-sample t-test. So it doesn't matter which way you look at it, but the point is the situation and what you have in terms of variables and the information that you have dictates what test you're going to use. Okay. So let's talk about different tests. A common test is test for group means. So the scenario that you have is you want to know, is there a difference in population means between two or more groups? Okay. Information you know, well, how many groups do I have? If you have two groups, you're going to use a two-sample test. You're going to use a two-sample test, but depending on whether you know the population variance or not, you're going to use the z-test or the t-test. The z-test is used when the population variance is in fact known. Now this occurs very rarely, but it's introduced in most statistical texts. If we don't know the variance, which is more likely the case in practice, you're going to use a t-test. Okay? And remember, for a t-test, you have a two-sample t-test that's unpaired versus a two-sample t-test that's paired. Paired t-test will be used for paired data. For example, if you measured observations before and after an experiment from the same people. If you have more than two groups, what you're going to use is a one-way ANOVA. Okay? And more specifically, you're going to use an f-test from the one-way ANOVA to determine whether or not the means are the same versus the means are different. In all of these tests, the null hypothesis would be that the two or several means will be the same, versus the alternative that at least one of those means aren't the same. Test of proportions. Okay? Scenario is you want to know if the frequency of categories in one variable depend on the categories of another. Okay? So unlike the test of means, we have categorical variables. Okay? Because it doesn't make sense to talk about means for categorical variables, but we can talk about proportions. Okay? Or you want to know if the distribution of a categorical variable is different based on the levels of another categorical variable. In either case, such a data would be organized in what's called a contingency table. What I've shown here is a 3x3 contingency table where race ethnicity is one group and then hemoglobin level is the other. Okay? And so the cells in the table shows the frequency or the counts of each occurrence. Okay? The way you test, or the appropriate test here that you're talking about, is are the variables independent versus are the variables dependent. So in this example I put here at the bottom, you're determining is hemoglobin level and race ethnicity independent or dependent, where the null is that they're independent and the alternative is that they're dependent. You're going to test this using a chi-squared test. And the chi-squared test is computed based on observed and expected counts of each cell. The degrees of freedom associated with this chi-squared test would be the number of rows minus 1 times the number of columns minus 1. So for this previous example, because you have 3 columns and 3 rows, the degrees of freedom would be 3 minus 1 times 3 minus 1, so that would be 2 times 2, so 4. Similar tests may also be called tests for homogeneity, but in either case, you're going to have a contingency table and you're going to use a chi-squared test. Goodness of fit test. So this is another application of a chi-squared test. The scenario you're going to have is you want to know, does your sample come from some hypothesized distribution? Okay. So for example, your data is results from a 6-sided die. So you have many rolls of a 6-sided die. And you want to know, is the 6-sided die fair? So what the data you're going to have is going to look like is the number of 1s you got, number of 2s you got, number of 3s you got, and so on. Okay? So if the die is in fact fair, you should get about the same number of 1s, 2s, 3s, 4s, and so on. Okay? So you're going to calculate a chi-squared test based on what you observed and what you expect and determine whether or not is this die fair. The null hypothesis would be that they are fair, or the die is fair, and the alternative would be that it's not, because you're hypothesizing that it comes from this distribution. A more practical problem would be to use it for continuous data to determine whether or not a sample comes from a normal distribution, in which case, because you have continuous data, you have to divide the data into intervals or strata, then compare the observed and expected counts using a chi-squared test in those intervals. Okay, so the test that we mentioned above will tell us if something is significant or not. So it answers the question, is there an effect of some kind? But sometimes we're interested in, well, how much is the effect, or what is the magnitude of the effect? This can be answered in different ways, but again, what you use to answer such a question depends on what type of variables you have. So if you have a continuous independent and dependent variable, and you want to know the measure of association between them, you're going to use a correlation analysis or correlation coefficient. On the contrary, if you have dichotomous independent and dependent variables, you're going to use either a relative risk or an odds ratio to quantify the effect. Okay. So let's talk about correlation a little bit. A correlation represents the strength of linear relationship between two continuous variables. This strength of relationship is a parameter known as the correlation coefficient. You might have seen it represented as Greek letter rho. A correlation coefficient ranges between -1 and 1. The more positive it is, the more positively correlated or positively associated the two variables are. The more negative it is, the more negatively associated or more negatively correlated the two variables are. Correlation coefficient is 0, okay, or very close to 0. That means that the variables, the two variables, are not correlated, meaning there's not any association between the two. And this is similar to regression in that you have two variables on a two-dimensional plane. So positive correlation would be equivalent to a regression with positive slope. negative correlation would be regression with a negative slope, and no correlation would be regression where the slope is almost horizontal. When you have dichotomous independent and dependent variables, a measure of effect might be relative risk or odds ratio. Okay? I'm not going to go into very specifics of when you should use relative risk and when you should use odds ratio, okay? Because I'm sure you covered that extensively in epidemiology. However, I will say that in general, relative risk is used for prospective studies, and many times the data would be organized in a 2x2 contingency table. In this 2x2 contingency table that I have, you're going to have some risk factor, that's your independent variable, and then some outcome, which is going to be your dependent variable. Both are going to be dichotomous, so yes, no, 1, 0, or such variables like that. You're going to have counts within the 2x2 contingency table. Okay, how many people have the risk factor and the disease, how many people have the risk factor but no disease, and so on. From here, you can calculate the relative risk based on these cell counts. Okay, a relative risk is the risk of getting the disease with the risk factor divided by the risk of getting the disease without. Okay? And so it can be calculated as A over A plus B and C over C plus D according to how I have labeled the cells. As I mentioned at the beginning, there are no calculations on the exam. If a solution comes up for relative risk, it will be in this form of equation format. Okay, so you'll see numbers for here, here, and here, and here. Okay. But this is a fairly common question to ask in addition to the odds ratio. So this might be something you may want to remember, how you calculate relative risk. Same thing for odds ratio. You're going to have a similar setup, okay, but again, in general, you're going to use odds ratios for retrospective studies, but the setup is going to be the same. The quantities you're going to measure are going to be the same. Okay, but with an odds ratio, you're talking about the ratio of odds of having a disease with the risk versus or over odds of having a disease without the risk. Okay, and you see the formula for odds ratio there. This is, again, something that probably comes up a lot on the CPH exam, so you definitely want to know. So risk and odds ratio, okay, they have similar interpretations, although they have vastly different applications. If the value of the relative risk or odds ratio is 1, then there is no association between the risk factor and the outcome. If it's greater than 1, there's a positive association, and if it's less than 1, there's a negative association. How do you check for significance? Very oftentimes for these, you're going to see a confidence interval. So you're going to see a value for relative risk or odds ratio followed by a confidence interval for that measure. If a confidence interval contains the null value of 1, then that odds ratio or relative risk is not significant. So for example, if I have relative risk of 1.2 with a CI of confidence interval of 0.7 to 1.3, that's not significant because it does not, or it does contain 1. However, if the OR is 1.5 and the CI is 1.2 to 2.1, that interval does not contain 1, so this odds ratio is significant. Moving on to some modeling techniques. Linear regression. So as I showed with correlation, linear regression and correlation are similar. However, correlation is used when you want to determine the association between X and Y and when you want to quantify the magnitude of that relationship. When you use linear regression, you actually want to model the relationship between X and Y. So you might use it for prediction in addition to just checking for association. At the very simplest, a simple linear regression will have one X and one Y. X is what I'm calling the independent variable and Y is what I'm calling the dependent variable. The model for this regression is just a straight line. Okay, I call it y equals beta 0 plus beta 1x, but this is no different than your algebra class when you had y equals mx plus b. There's a slope and there's an intercept. Okay, the way this works is that your data are points on two dimensions. Okay, so if you look at the graph that I presented here, the points that you see on the graph are your data points. That's what you observe. The idea is to fit a single line over those data points that fits this data pretty well. And you're going to use that, or you're going to do that through the method of least squares. Once that line is, pardon, I'm getting ahead of myself. Once that line is defined, then it's easy to find an estimate for the intercept. That's where it crosses the y-axis. And it's easy to estimate the slope. That's only the rise over run of this line. Okay. We can measure how well the line does in fitting the data. Okay. I'm not going to go into too much details for this, but graphically we have three sort of distances. Okay. We have a distance from the average of y to the point itself. So average of all y's to your observation y1 here. Okay, that distance is how far away my sample mean is away from the observation. In a sense, that's the worst case scenario. If I didn't know x at all, I would have to use y bar to estimate the mean of y. So in a sense, I'm starting out with this difference that I have to explain. But by using the regression line, I get closer to that line, or the point. So my regression line is here, so I get from this point to the original observation. My distance from the observed point to my predicted point here decreases from what it was with y bar. Okay? Because I've explained this much from y bar to my line, in terms of how much variability was to explain. Okay, so with this amount explained, you still have some unexplained, and that's this portion here. So what you've done is divided what you needed to explain into some parts that you can explain, what you can't explain. The more you can explain, the better the fit the line is. Okay, and we can quantify that fit using a quantity called the coefficient of determination. It's often denoted as capital R squared, and it quantifies how much variability is explained by your line. Okay, so in a sense, how well is your line fitting the data? There's a connection to correlation coefficient. If you square the sample correlation coefficient, you're going to get the coefficient of determination. That's why it's called R squared. The main parameter of interest in a linear regression is usually your slope parameter, beta 1. Okay? The way we interpret beta 1 is it's the amount that y changes when x increases by 1 unit. Okay? So if x increases by 1 unit, y changes by a factor of beta 1. So for example, if y is BMI and x is calorie intake, beta 1 would represent, on average, how much increase would there be in BMI for 1 unit increase in calorie intake. If beta 1 is positive, that means x and y are positively associated, or x and y are directly proportional. It means that as one goes up, the other goes up with it. If beta 1 is negative, or inversely proportional, meaning as x goes up, y goes down. And if beta 1 is 0, then that means that y doesn't depend on x at all, meaning no matter what values of x you have, it doesn't really predict y. There is another parameter, beta 0, but that's usually not of interest to us. Okay, so you use linear regression when the outcome Why? The dependent variable is continuous. Okay? But in public health applications, you're going to see a lot of situations when the outcome or the dependent variable is dichotomous. Okay? Whether you have the disease or not, whether you meet a certain threshold or not. When the dependent variable is dichotomous, an analogous to linear regression is something called a logistic regression. To remember when determining should I use linear regression or logistic regression is what type of an outcome variable, what type of a dependent variable do I have? If I have a continuous outcome, then I should use a linear regression. If I have a dichotomous outcome, then I should use a logistic regression. In this case, because the dependent variable is dichotomous, we model the probability P of getting 1. So one of the categories of the dichotomous variable, and the model looks similar to your regression as before. The main reason logistic regression is so popular in public health is because by taking that beta 1 coefficient from logistic regression and doing the e to the power of beta 1, we can actually show that that's the odds ratio for this dichotomous dependent variable when x increases by 1 unit. Because of that analogy to the odds ratio, and because odds ratios are used as effects so much in public health, logistic regression is very popular. Okay. Multiple regression. Okay. Some of you might have seen it as multiple linear regression, but actually the term multiple regression only means that you have more than one independent variable in a regression model, regardless of whether you have linear regression or logistic regression. Okay? So the regression models that we saw above, both with linear and logistic, only had one x, okay? Because that's the x or the independent variable of interest. However, there may be other variables that affect the relationship between your x and y. You might only care about x and y, but the relationship between them may depend on other things. Okay? The example I used above was x was calorie intake and y was BMI. Well, we know that a lot of other things affect not only BMI, but also calorie intake, like your physical activity, your environment, social factors, etc. So we have to control for those when we are analyzing the data, because if we don't control for it, we're going to get results that may not be true. So when you have such variables, the conventional thing to do is to include them in the regression model as additional independent variables. Okay? So if you have a linear regression, in addition to the x that you already had, you're going to have other x's in the model, here, 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 and so on, that are serving as control variables for your model. Okay, so you may not have any interest in the other independent variables, but you need to put them in your model because you know that it affects the relationship that you're trying to study. Same thing with logistic regression. Again, you might only have one dichotomous dependent variable and an independent variable of interest, but if there are other factors that influence that, you should include them in the model. Okay? In terms of linear regression, linear multiple regression, graphically what happens with additional independent variables is that you get a plane instead of a line. So if you just have x1 and x2, that would be a plane in three-dimensional space. If you have another independent variable, you're going to have four-dimensional space, which we can't draw, but that's the concept graphically. Okay, we're close to the end. So survival analysis. Okay, as I mentioned, this may be a topic you might not have covered, so I have a few slides on this. Okay, survival analysis is a collection of statistical procedure used for outcomes that is time until an event. And remember what we said time until an event means. It means that you have an event or you have a variable that measures whether an event occurred or not. So did somebody die or not? Did somebody get diagnosed with the disease or not? Something like that. In addition, you are measuring the time it takes for that individual to experience this event. Okay? Now, time could mean years, months, weeks, days. It's the time that it takes from the time you start looking at this person until this event occurs. Okay? Another way to look at time is their age. Okay? You can think of when they're born as their start of their time, and then how long does it take for them to experience the event. Okay? So from the time they're born, how long do you have to wait until they are diagnosed with heart disease, for example? Okay? And an event means any event that you are interested in studying. Traditionally in survival analysis, an event is a death. That's where this came about. But it could be disease incidence, it could be relapse from remission, it could be recovery from an injury, or any other occurrence of interest. And it doesn't have to be a negative event, it doesn't have to be a positive event. It's just an event that we are trying to study. Okay? If the event of interest is the only information you have, meaning you don't have the time until the event, then you just have a dichotomous outcome and you have to use logistic regression. However, in addition to knowing whether an event occurred or not, if you have the time until that event, you can use survival analysis. Okay. Some applications for survival analysis. You might study leukemia patients in remission over several weeks to see how long they stay in remission. Or you might study a disease-free cohort of individuals over several years to see who develops a certain disease. Or you might monitor a parolee, so they are paroled from prison, and then time until they're rearrested. Or you might follow heart transplant patients until that person eventually dies. Okay, so these are some of the applications that you might see for survival analysis. Many of this tends to be clinical in nature. One public health application that's gotten lights recently is hospital readmissions. Under the Patient Care Act, there is a penalty for repeated 30-day readmissions into hospitals, so you might track the time until somebody is readmitted into a hospital. So when we're talking about survival analysis, we have to consider a key concept called censoring. Okay? So ideally, when you're studying someone's event until, or time until an event occurs, you can observe them from beginning until the event eventually occurs. However, in practice, it doesn't occur that way. People come into study at different times. People experience events at different times. People may never experience the event. Okay? A leukemia patient in remission may never come out of remission. Okay? So when those things happen, we have to take care of that in our analysis. And that's handled by a concept called censoring. Okay? Censoring occurs when the exact survival time, so the time until event, is unknown. Okay? This could occur usually because individuals are lost to follow-up, meaning we lost contact with them, or like a parolee flees the area and you're not able to locate him, or an individual is withdrawn from the study. Okay? An individual could be withdrawn from the study, for example, if they were in the disease-free cohort being followed until heart disease, but they unfortunately died in a car accident. So they died, but they didn't die because of the cause you're looking at, so they have to be removed from the study. When you're talking about censoring, there's three types of censoring. There's right censoring, left censoring, and interval censoring. Right censoring, which is the most common, is the situation when you know when the survival time starts. So you know when you started observing them, but you don't know when they experienced the event. Okay? Or more practically, your study ends before this person experiences the event. Okay? Left censoring is when you don't know the start. So you don't know when they acquired a disease or when the time started. So for example, if you're looking at survival time of an HIV patient, that survival time should start when they were first infected. However, you may only know that a person's infected once this person is tested. So your actual time will start from the time that they were first tested or tested positive. But the true time would have started when they were actually infected. Interval censoring occurs when the exact time of an event is unknown within the interval. So this happens like you are observing something every week, but someone died somewhere in the week, so you don't have the exact day that they died. Okay? Graphically, it looks like this. So the first person, this blue line here, is when we start observing. This is when the time starts. Okay? This first person, we observed and they experienced the event. They died. Okay? Within our study period. So this person is not censored. This person here, the second one, we started observing. Our study ended at this second blue line. Then this person eventually died. Okay? In general, once the study ends, we don't know if this person died or not. So for our purposes of the study, this person was right censored because they didn't die by the time the study ended. Similarly, this third person didn't die during the study period, and this person never died. Okay, but this person is treated exactly the same as this person above because whatever happens after the study, we don't get to observe. This next one is less censoring. So his time started somewhere over here, but we weren't observing him then. Okay, and then eventually he died during the study. So this is a less censored observation. Okay. And then the last observation, we were observing him, but something happened where we couldn't observe the exact time that this person died in here, but this person did die. This is known as interval censoring. Okay. Why do we use survival analysis? We use survival analysis to model the survival experience of a population. Okay? Survival experience is captured by something called a survival function or survival curve. The survival curve is something that starts at 100% because everyone is either disease-free or alive or they haven't experienced the event at the beginning. But as time progresses, more and more people experience this event. And theoretically, eventually everyone experiences the event. Okay? That's in theory, but in practice, because not everyone experiences the event, our estimate will look like a step curve or a step function, okay, where we start at 100%, but every time someone dies, we go down because our proportion alive goes down, okay, and we keep on doing that, but when our study ends is when we stop observing. So this curve, this step function, is not going to go all the way down to 0. Okay? It could, but if not everyone experiences the event during the time we were studying them, it will not go down all the way to 0. One common way of estimating the step function that you see is called a Kaplan-Meier estimator. Okay? And the curve that I've shown is sometimes called the Kaplan-Meier curve. So a Kaplan-Meier curve can be used to visualize the survival experience of a group of people, depending on what you're looking at. Okay. Now, if you have more than one group, for example, one's getting a treatment and one is getting placebo, and you want to compare their survival experiences, you could do 2 Kaplan-Meier curves, like I've done here. Okay. So one group is getting the intervention, the other one is getting standard treatment. Now visually you might be able to see that the survival experience of this pink line up here is better than the survival experience of the blue line down here, because this one goes all the way down to 0, but this one stays around 40-some%. Okay? If we want to statistically compare the survival experience of these two, we have to conduct a test. Okay? That test is called a log rank test. The test hypothesis is that the null is that the survival curves are the same. So both groups have equal survival experiences, versus the alternative that one group has a different survival experience. Now this method works for more than two groups as well, but just to illustrate, I've shown you two groups here. Okay, so if the test rejects, one group is doing better than the other group. Okay, in the remaining time, I want to talk about some of the miscellaneous topics that I haven't discussed, and these will go fairly quickly, and then at the end I will entertain any questions that you may have. Okay, so we talked a little bit about reliability and validity, but just formally. So reliability of a measurement is the overall consistency of a measure. So a measure has high reliability if similar results are produced under similar conditions. A common value to quantify reliability is Cronbach's alpha. This Cronbach's alpha, it has nothing to do with the significance level alpha. That's just what it's called. Cronbach's alpha varies between 0 and 1. Higher values of Cronbach's alpha indicate higher internal consistency. Reliability is usually what we can measure and what we can show. However, high reliability does not necessarily mean that the measure is accurate. That is, it's not necessarily valid. Validity is much more difficult to show, but a validity of a measurement is the assessment of the degree to which a measure represents what it's supposed to measure. Okay? So, very simply put, it means that is the measurement correct? Okay? A measure could be reliable but not valid. Okay, so let's go back to that bathroom scale example that I mentioned earlier. So suppose someone weighs 200 pounds. So this is true. That's their true weight. And this person gets on a scale 20 times. Okay? Each time the scale reads 250 pounds. Okay? Without any deviation, it reads 250 pounds every single time. This is a highly reliable measure because it is very consistent under the similar circumstances. Okay. However, this scale is not valid at all because this person really weighs 200 pounds. So for this scale to be valid and reliable, it needs to read about 200 pounds every single time. Okay? And in general, if you don't have reliability, it can't be valid. Some people will disagree, but for all intents and purposes, an unreliable measure cannot be valid. Confounding variables. A confounding variable is an extraneous variable that distorts the true effect of the independent variable, the exposure, on the dependent variable. Okay? Graphically, it looks like this. For it to be a true confounder, the confounder has to affect both the x and the y. Okay? For example, calorie intake may be positively associated to BMI. So exposure would be calorie intake and the outcome would be BMI. However, it would be confounded by the amount of physical activity you do. So somebody who exercises a lot would have lower BMI, so the outcome is affected. But somebody who does a lot of exercise may also eat more because they need more energy. Okay, so it might also affect the exposure. The way you control for confounding is either through stratification, meaning once you've identified a variable as a possible confounder, you conduct separate analysis for each level of that confounder. So for example, you thought gender is a confounder. Well, then you need to conduct a different analysis for males and then different analysis for females. The disadvantage to stratification is that you need a large enough sample size for each of those categories to be sufficiently large. And you need to categorize continuous confounders. Okay? For example, amount of physical activity might just be minutes per day. Well, you have to categorize that if you want to stratify. Okay? And it's also difficult to control when there are multiple confounders because every confounder means more strata. And then that's going to result in sample size issues, or it may not even make sense to analyze so many strata. So a more conventional way of analyzing things with confounding is to use a regression model. Okay, and we talked about this a little bit. So if you have a confounding variable, just add the confounders to your regression model as additional independent variables. Okay. You may only be interested in the relationship between the main independent variable and dependent variable, but the confounders can be interpreted in the same way as well. The advantage to using regression is that the confounder can either be continuous or categorical. It doesn't matter. Effect modifiers. So effect modification occurs when the effect of an independent variable on the dependent variable varies differently depending on the level of the third variable. Okay. That third variable is called an effect modifier. In the two graphs that I have, the first one shows that there's a positive association between X and Y for both men and women. Not only that, it shows that the rate of increase, okay, the effect size, is the same for men and women because the slopes are the same. However, in the second graph that I have, you see that the men and women have different slopes, meaning the effect of X on Y is different for men and women. In this case, gender would be an effect modifier. And we need to control for this, or we need to model this using what's called an interaction model, or a regression model with interaction. That means you add a product term as one of the independent variables, but just keep in mind, you don't have to know that specific, but just keep in mind an effect modifier can be modeled using an interaction and a regression model. Think a few more and I'm done, but counting distribution, okay, a binomial distribution models the number of events out of n observations. A Poisson distribution models the number of events out of infinite observations. Okay? But in practice, the number of observations will not be infinite, so when do you use Poisson? Okay? The key word that I said before is the event is rare. So if what you're counting is a rare event, a Poisson distribution may be more appropriate, or if you're modeling the number of events over time or space, then you may want to use Poisson distribution. Well, thank you for listening. I will entertain any questions if you have any.
Hi, Sumi. We have a question. Is it safe to say that if you have a nominal and ordinal data, you have a non-parametric test, and if you have an integer or a ratio variable, you have a parametric test?
That's a very common way to handle it. So the chi-squared test, the contingency table chi-squared test that we talked about, that is called a non-parametric test because it doesn't depend on any parameter about the population. So in general, if you have ordinal or nominal data, you tend to use a non-parametric test, as opposed to if you have continuous data, which is either an interval or ratio measurement scale, you're going to use a parametric test like t-tests and z-tests and things like that. Very good question.
There's a question asking for you to go over the previous slide before central limit theorem.
Okay. This one?
It doesn't specify.
Okay. So one before. So z-score. So a z-score has a couple different uses, but technically speaking, a z-score means that you take your observation, which came from a normal distribution, you subtract the mean and divide it by standard deviation. That will produce another normal distribution with mean 0 and variance 1. The reason why that's useful is once you standardize it, the quantity is unit-free. So you can compare a z-score from any type of measure because now you're talking about in terms of how many standard deviations is it different instead of the original units. So for example, it doesn't make any sense to compare someone's weight in pounds versus kilograms because those are two different measures. However, if you standardize them, those are unit-free. So now you can compare someone's z-score from pounds and someone's z-score from kilograms. Okay. So that's in theory, but the more practical use of a z-score is standardization for tests. So whenever you do a hypothesis test for means, you're going to take your x bar and subtract the mean and divide it by the standard deviation. This concept of z-score shows you that by doing that standardization, you get another normal random variable, which you can calculate a p-value from. Okay, very good question also.
When do you use the Fisher's exact test?
Okay. The first is a alternative to the chi-squared test for independence. Okay. It's usually used for a 2x2 contingency table when the expected counts are low. Okay. So what I mean by expected counts are low is that you usually have a low sample size, and so the expected counts in each cell don't meet, the general rule of thumb is 5. So when you have low expected counts, you want to use a Fisher's exact test. If you have sufficiently large sample size in cells, which will produce sufficiently large expected counts, then you can just go ahead and use the chi-squared test for independence. Good question.
I'm not seeing any other questions. Thank you very much, Sumi, for presenting for us today. The slides will be available on the website, and we'll also be emailing them to you. And if you have any other questions, feel free to email info@mbphe.org, and I'd be happy to send them to our presenter today who can respond to you. Thank you all very much, and have a great day.